So welcome. So this is the next chapter, which is on inductance. And just to have a quick look, we're going to talk about big ideas. When a current flowing around a circuit changes, the circuit induces a back EMF on itself. So in a nutshell, circuits will fight you. When you try and turn them on, they will try and turn themselves off. When you try and turn them off, they'll try and keep themselves on. It's just inevitable. Which is why when they have big power outages, they can't just flick a switch downtown and turn everybody's electricity back on. They've got to do it in stages. When a solenoid is used as a component in a circuit, it is called an inductor. So we might actually try and make a component which has a magnetic effect, rather than for its electronic properties, rather than for its magnetic properties. And that's called an inductor. And it turns out it's very... At low frequencies, it's like it's not there because it's just a piece of wire. At high frequencies, it kills you. So it tends to be the opposite of a capacitor. Whereas capacitors kill you at low frequency and they let you pass at high frequency. An inductor will kill you at high frequency and let you pass at low frequency. So they work hand in hand together. And then inductors cause transient effects on current flow, and this is analogous to the time varying charge on a capacitor. And so we look at these three bits. Okay, so here's a circuit. I drew it in perspective so you could see the magnetic field kind of going into the table, if you like. It consists of a switch. Let's get this thing up here. There's a switch here. There's a resistor here, there's a power supply there. It's a DC power supply. So all that happens is, at the moment nothing's happening because there's no current can flow. And then we close that switch. And when we close that switch, the circular motion of the electric current causes a magnetic field. And if we use the right-hand corkscrew rule, we can say, well, okay, the current which comes out of the positive, the current flows in that direction. So I put my thumb up the page and I curl my fingers. And you can see that the current goes, the magnetic field goes out of the page and into the page like that. Can you see that? It forms this loop. When you get a current carrying wire, you get this circular magnetic field that goes around. And the sense of it is that if the current's going away from you, the magnetic field is like that. And that's just the right-hand corkscrew rule. Okay? So that's what those two red symbols are indicating. They're indicating that the B is going into the page on the right-hand side of the wire, or in the inside of the loop and out of the page on the left-hand side. I've basically taken a line through there, and that's going into the page there and coming out of the page there. And that's what I'm showing here, down here. Well, if I go around the corner, and now my current's going down here, I get the same effect. And if I go through the resistor, I get the same effect. And if I go through my bottom piece, I get the same effect. So this red is all what's originally done by the original EMF. All the red stuff is what the original EMF is causing to happen. Okay. So we say when we switch is closed, the current driven by the battery increases in time. Whenever you get a changing magnetic field, you induce a back EMF. You induce a back EMF. So the magnetic field through the circuit loop, due to this increase in current, also increases in time. So the increase in current causes an increasing magnetic flux. This increase in magnetic flux, well, according to good old Lenz's law, whatever you try to change, I'm going to fight you with. So according to Lenz's law, we're going to try and turn off what we just did. And so whereas we had a magnetic flux line going into the page here, we try and make one coming out of the page. And into the page there, we try and make one coming out of the page and into the page there. So whatever we try and do, we do the opposite. And it turns out, well, the way you do that is you induce a back EMF. So the blue, let's see if I can change my pen color. Let's have a look if I can change my pen color. Maybe I can, maybe I can't. Let's look. Can I? Pen color. Give me a pen. So my blue magnetic flux lines, this is the response of the system using Lenz's law. And that can be summarized as we can imagine that is caused by a back EMF. It is a EMF that is like from a battery that we have induced into existence. There's not really a battery there, it's just, if there was a battery there, this is how it would behave. So we say this increasing flux creates a back EMF. The EMF has a sense, a direction, that creates a current loop that creates a magnetic field that opposes the change in magnetic flux, and that's good old Lenz's law. So the source of EMF is opposed by the induced EMF. And so these two guys fight each other. Now, frankly, what's going to happen is the red original EMF is going to win, because as this thing slows down, so the back EMF decreases and decreases and decreases. So rather than being able to, if this is current versus time, rather than being able to just close that switch and increase my current to the maximum allowable given that resistance and that EMF, what happens is I approach that value. We've seen this before with capacitors. So what happens is I have a time constant like I had before, etc., etc. That's where we're going. Okay. But it's significant to realize that the circuit, you know, before we did a magnet going towards a coil or a magnet leaving a coil, and then we had one coil talking to another, and you turned the current up in the coil, and it was like a magnet approaching. This is a circuit messing with itself. And it tends to be most significant when you have big currents, because you get a big change in current in time, or you have very small geometries. So this tends to catch you out if you're in the power business, and it tends to catch you out if you're in the integrated circuit business. And in fact, they design that so that nowadays integrated circuits are not designed by people; they're designed by machines, by computers. And as part of their algorithm, they'll have an algorithm in there which will try to minimize the amount of flux going through loops. And one way you can do that is, rather than having your circuit like this, why do we do this? Let's put our battery, let's put our switch. If you have to have it looking somewhat like this, just minimize this area inside, as opposed to maximizing the area inside. And that can help. So it's kind of interesting. This is without using it. This is not deliberately using it. This is like living with it. So we can talk about a self-induction in a solenoid. So we have when the current flowing through a solenoid changes, a back EMF is established. The back EMF is always proportional to di by dt. It's the rate of change of current. We say the EL, this is the induced EMF. Sure, it shouldn't really be a big L with a little e, but you know, it's the size for the little E is tiny and the L is bigger. It's just the way the font goes. So my induced EMF is equal to minus n, the number of turns, d phi b by dt. Remember that from before the break? And this is equal to minus L di by dt. So let's just remind ourselves of those two equations. So my induced EMF is equal to minus L di by dt. And it's a bit like, when you think about it, it's a bit like E or V is equal to Ri. So the L is acting a bit like a resistor. It's like a component. Yes?
What's N?
N is the number of turns in a coil. So for the solenoid, it's going to be a number of turns. L is called the inductance of the solenoid. The inductance is measure of the resistance to the change of current. So L is equal to N phi phi b over I. Where did that come from? L is equal to, well, where did that come from? L is equal to, oh, it's by definition, I think. L is equal to n phi b over I L. Oh, yeah, you get it from there. Yeah. Cool, okay. And so in SI units, the inductance is in henries. So an henry is a volt second over amp. What am I showing you in this diagram to the side? Just basically I'm showing you that you basically induce a back EMF. So inductance in a solenoid, magnetic field of the solenoid is given by B equals mu naught N over D. D is the length times I. We can't use L anymore for length because inductance is using it, so we're running out of letters again. It's just the way it goes. Magnetic flux through each turn is, well, phi is equal to B times A, which equals mu naught N over D I A. And if we remember that L equals N phi B over I, we get minus mu naught N squared A over D, where A is the area, N is the number of turns, D is the length of the solenoid. This has turned out to be a bit interesting, actually. So L is equal to mu naught little n, which is the number of turns per unit length, times the length. So this is number of turns per unit length. Whereas this is number of turns. So little nd squared over d times A, which equals mu naught N squared A D, which equals mu naught N squared. Well, A times the area times the length is equal to the volume. So L is equal to mu naught N squared V. So let's just stop and think about this. I get a bigger inductance if I have a bigger volume. That's interesting. Doesn't matter. I could have a shorter solenoid as long as it's somewhat. As long as it's not just a coil, as long as it is solenoid-ish, I could make it shorter with a bigger area. And if I could cram in more turns per unit length, that really pays off. If I could double my number of turns per unit length, I would quadruple my inductance. So this is not the kind of equation, I don't need you to know this equation, but I need you to know what the symbols stand for, because I could turn around and say, well, do you remember that L is equal to mu naught N squared times V? Plot a graph of the inductance versus the volume. And then you've got to recognize V equals volume, L equals inductance, and know how to play with it. You don't have to remember that equation. Just when given that equation, you've got to know what it stands for. You know, okay? I don't remember that equation. It's like. So, okay. Next bit, applying EMF to an LR circuit. So, consider a circuit below, consider closing the switch S1. So we got these two switches. We'll get to that in a minute. We did the same thing with capacitors. We wanted to charge and discharge. Well, now we're going to think of it in terms of energize and de-energize. So we have a battery, we have this guy's open, if we close this guy, suddenly a whole bunch of current will flow. The current will be limited by my resistance, not limited by the inductor. The inductor is like very low resistance. That's the idea behind it. If you just put a DC through it steadily, you'd hardly notice it's there. Whereas this is a resistor. This is like genuinely there. And what happens is that, well, you might think, well, okay, we're going to immediately go to our value that's allowed by this resistor. If this effectively is no resistance and this has all the resistance, then just V equals IR. So I equals V over R. So my current should immediately go there. But what we find is that's not actually the case. As we rapidly increase our current, then this guy says, oh, Okay, di by dt. I'm going to establish a back EMF to fight you. And what's going to happen is I'm going to lose, but I'm going to put up a battle. So I'm going to slow you down. So rather than immediately going to the value, you're going to approach the value. And it turns out you can do a Kirchhoff's analysis, but basically using Kirchhoff laws, we get that the EMF minus IR minus L di by dt equals 0. When you solve it using differential equations, you get I is equal to E over R 1 minus e to the minus t over LR. Now, let's, for the fun of it, we add Q is equal to E times C. Remember? That's just from our charge equals VC. V in this case is the EMF. And then we modified it by charging by saying it was 1 minus e to the minus the time over, and the time constant in that case was RC. So that was my capacitor's equation. And can you just see the analogies? It's kind of like, well, the maximum current that goes through my circuit would be V over R. So rather than, so I have E over R because E is my EMF. And it's modified by this 1 minus e to the minus t over my time constant. My time constant in this case is L over R. So again, I've saved myself some work here. It's not like it's a new equation that I've never seen before. By doing the analogies, I can turn around and say, oh, okay. It looks somewhat like the old equation. And I can see how it works. There's my maximum value, and it's modified by this guy. Here was my maximum value, and it's modified by this guy. What I got to kind of remember is that this is in terms of current, whereas that was in terms of charge. But current for an inductor behaves like charge for a capacitor. Time constant, of course, is a nice way of finding out how long it takes you to get to the 63rd percentile of what you're going to get to in the end. So how long does it take me to get to 63% of my maximum current? So again, it's a really good way. If the inductor is 10 farads and the resistor is 5 ohms, then my time constant will be 2 seconds. So it gives me an immediate feel for how quickly this system rises. So it's very nice. And by analogy again, I can say, well, if that was for the energizing, what's it like for the de-energizing? So what we do for that is we open up this switch here, and then we close this guy just to let the current kind of flow back where it wants and everything to equilibrate and all that kind of stuff. And what we find is the current then falls off like that. And we get I is equal to, again, the maximum value modified by this guy. Okay? And again, I have discharging the capacitor is like de-energizing the inductor. Okay? And like before, what are the good questions I can ask you? What is the time constant? What is the value of the current at this particular time given these circuit conditions? So just expect it, Conceptual question here. Which circuit has the biggest inductor? Well, we're looking at the graph, aren't we? And this thing has been 0 until you turn it on, and then I think it would go straight up immediately to the maximum value, but it doesn't. It gradually approaches it, but one of these gradually approaches faster than the other. The blue circuit, I'm sorry if you printed it out in black and white like I do in my notes. I can't tell which is which I think is why I put down blue and red. But basically, the blue circuit basically has a bigger inductor than the blue circuit has a smaller inductor than the red circuit. How do I know that? If there was no inductor, it would immediately go to the maximum value. But because there is an inductor, it takes longer time. And if I had an even bigger inductor, it would take even longer. So which circuit has the bigger inductor? And it's the red circuit has the bigger inductor. And then at time t equals 0, switch S1 is closed. Switch S2 is open. At t equals 10 seconds, switch S1 is closed, switch S1 is open. And I think that's what I'm saying here. This is what's going on. I thought it was a calculation, but that's telling you what's going on. So let's do a little bit of calculations on this. What would be the time constant? So tau is equal to, what was it? L over R. And, oh, excuse me. And so we say, okay, this is going to be a 5 Henry inductor, and this would be a 9 ohm resistor. Oh man, trust me. So, oh, actually no, because I actually do this for a living, I brought my little calculator with me, which is all right. So this would be 9 divided by 5 equals, 5 divided by 9, 5 divided by 9 equals, so that would be 0.55, so this would be 0.55 seconds. Okay. Consider a circuit that consists of a 2-volt battery, 4 Henry inductor, 7 ohm resistor that are connected in series. What current flows through the resistor 30 seconds after it's closed? S1 is closed, so again I'm energizing. So I say, well, my I at a given time is equal to, what would my maximum current be? V equals IR, I equals V over R. Well, here we don't talk about V, we talk about the EMF over R. That's my maximum value. And for charging or energizing, it's 1 minus e to the minus t over tau. So that equals E over R, 1 minus e to the minus t, and then my tau is L over R. So then I go, well, my current at this time is equal to, now I can put numbers in. So I'm going to get 2 volts over 7 ohms, 1 minus e to the minus, and this is 30 seconds. Oh, I think I've gone and walked off a cliff here, but well, that's 30 seconds over. What is the L over R? 4 over 7. Is that right? So let me just have a quick look. So just for a laugh, let's work out what our time constant is in numerical values. So our time constant, we'll do it over to the side. Our time constant is equal to L over R. Yeah. So in this case, our time constant is equal to L, which is 4, divided by R, which is 7, which equals 0.57 seconds. So, with that in mind, what do you think the answer is? 30 seconds. It'd be the max, isn't it? So what I've done is I've missed a conceptual bit. But now let's just work this out and just confirm that it's, if not the max, as close to it as possible. So I'm going to go 30 divided by parentheses 4 divided by 7. Let's let it do that bit first. So I get 52. So I go that e to the x minus second answer. Let's see if it can do that. I get that. I get something to the minus 23. I think I know which way this is going. 1 minus second answer gives me 1. And then times 2, enter, divided by 7, enter. So I'm going to get, long way round, I should have got there immediately, maximum value 2.8, 2.9 amps. Or by concept, T is very, very, very much greater than tau. So I at a given time equals I max. I max is equal to E over R, which equals 2 over 7, which equals 2.29 amps. You know, so even though I was a bit asleep at the wheel, and I didn't immediately see that this time is much longer than my time constant, even if you don't see it, you can work it out if you do the math right, yeah? But it's nice to see it. Guess what's coming up next? Oh, I didn't even do one. Shame on me. Well, we just did it. As always, I'm always looking for decent quality questions to come up on the test, and that's a decent quality question. It's like, you know, especially working the time out, working the value out at a given time. So know that equation and be prepared to use it. Okay, so then we're going to go on and do a couple more bits. What's the energy inside a inductor? And this, I would characterize this under, again, this is not an equation that I remember, but if I gave it to you, I'd like you to be able to figure it out. I don't know why I don't remember it. You know, it's very reminiscent of many other equations. I guess it's just, you know, in the scheme of things, I've just not done much work with it. But what we say is, okay, if the inductor stores energy, how much energy does it store? And what we say is a battery must do work against an inductor to establish an electric current. Part of the energy supplied by the battery appears as an internal energy in the resistor. The remaining energy is stored in magnetic field in the inductor. Kirchhoff's laws give us that our EMF minus IR, that's the potential difference because of the resistor, minus L di by dt, which is the potential difference dropped across the inductor, equals 0. That's the good old loop rule. And multiplying both sides by I, sorry about that, by I, gives us I squared minus Li di by dt. And if we remember that du by dt, the rate of change of energy, equals Li di by dt, we get that the total energy stored in the inductor can be obtained by integrating this. So integrate. And we're going to get the integral of Li di integrate with respect to time, and so L, and we end up with that. And I just don't know why. It's kind of interesting. What it says is that for any given current, my energy stores with the inductor, so twice as much inductance, twice as much energy. And then for any given, well, for a given inductor, my energy scales with the current squared. So if I double the current, I have 4 times the energy stored. I suppose the reason why I don't care that much about it is because we don't tend to use inductors very often for storing energy. You know, we tend to use them for their transient properties. Mutual inductance. So all this is saying is, it's saying, look, you can induce a back EMF in your own coil, in yourself. Well, if you're near another coil, you're also going to induce a magnetic back EMF in that, because you're going to bathe it in your magnetic field. This is a bit like we had the solenoid and we had the solenoid, and we turned one on and we said, what happens to the other one? It's that same kind of setup. Remember we just did in the last chapter, I think it was. We did that, and then we said, which way will the current flow given these geometries? We're kind of doing that. We have one coil here. We've got a loop in this case, and one coil here, and we're saying, well, what's the crosstalk between the two? There is crosstalk, and there's a very simple solution to this, which is transformer. That's what we're heading towards. And frankly, I want you to know about this, but that's all. I don't want you to know the equation. I don't care about the equation. If you look back at some of my old tests, when I would give an equation sheet, I would ask about this because, but we've got so many equations now. I'm kind of like, I'm trying to be honest about which ones I do use a lot, which ones I use a little. So this is another one to put down and remember what the things stand for, but don't go, you don't have to remember it. M is like L. It's the mutual inductance as opposed to L, which is just the inductance. So when magnetic flux in one circuit loop varies because of time varying current in a nearby current element, we call its mutual inductance. Consider two closely wound wire loops, etc., etc., etc. We get to that. So know it's there, you know. Know it's heading towards a transformer. If I show you the equation, you know that the M2 is the inductance in coil 2, N2 is the number of turns in coil 2, I1 is the current in I1. Okay. It's not all about coil 2. It's partly about M1. And again, the same kind of goes for this. It's like, let me just see where I go on this. Yeah, the same kind of goes for this. I take my mutual inductance and I just play with my EMF, and I get this, and I say in mutual inductance, the EMF induced in one coil is always proportional to the rate at which the current in the other coil changes. Mutual inductance caused in one coil is equal and opposite to the mutual inductance caused in the other coil. So yada yada yada. I don't want to raise it because I want you to know it's there in the book and it's a thing. So I'm reluctant just to blow it off completely, but don't spend much time on it. This is heading us towards something which I think is going to be quite important for us. And there's a lot of math, and again, I just want you to, at this point, I just want you to get the over picture. So now, we are going to take an inductor, and we're going to take a capacitor. We're going to charge up the capacitor. So the capacitor is going to act like a source of energy. Not just act, it will be a source of energy. And the capacitor is going to want to discharge, but it's going to have to discharge through an inductor. Now, this is a theoretical circuit. You can't make a circuit like this without having some resistance. But let's just for a minute imagine we can. And the analogy I'd use is, if we have a mass on a spring, we don't worry about air resistance unless we're told to worry about air resistance. So in this case, I have an inductor and a capacitor. Don't worry about resistance unless you're told to worry about resistance, because it fulfills the same role in both cases. Conceptually, assume the capacitor is fully charged, so initially all the energy is stored in the capacitor, so it's charged. When the switch is closed, the capacitor discharges through the inductor. Well, it discharges by moving charge, which is a current, and the rate of flow of charge will vary. So we already know there's going to be a back EMF. A current flows through the inductor. The current reaches a maximum value as the capacitance becomes fully discharged. At this point, no energy is stored on the capacitor because there's no charge there anymore. And all the energy is stored in the inductor because maximum current means maximum magnetic field, and maximum magnetic field means maximum energy storage. So we took all our energy from the capacitor and put all our energy in the inductor. Okay? But the current's flowing. So now we're charging up the opposite direction. So the current flow continues at a slower and slower rate as the capacitor becomes charged in the opposite polarity. Eventually the capacitor is fully charged in the opposite polarity, and the current flow through the inductor is zero. So at this point all the energy is stored on the capacitor again. And then it reverses. So it's an oscillation. The current flows one way and charges the capacitor the opposite sense, and then flows back and charges the capacitor in the opposite sense, and then flows back and charges the capacitor in the opposite sense, and flows back and charges the capacitor. So you're changing the charge direction on the capacitor, but every half cycle you're getting complete charge on the capacitor, and in between you're getting maximum current flowing through the inductor. And that will continue forever unless there is some way of getting energy out of the system. And resistance is what gets energy out of the system. Resistance changes current flow into heat, and heat dissipates. So if I don't have a resistor and I plot current through the circuit in time, I will see that. Just a perfect sinusoidal, simple harmonic motion oscillation. And if I have resistance, I will see, I can't draw it very well, but you know, like that, just like damped oscillations. And I bet, like with damped oscillations, the frequency is slightly different. I bet it's just completely analogous. Here I'm trying to show that. I'm not doing it very well. This is my diagram. It's doing what's in these words over here, but it's trying to show the analogy between the oscillations backwards and forwards and the. So this is the electrical equivalent of the mass on a spring. We're going to use that to our advantage. So a page full of math. Total energy in an LC circuit. Okay, so now we've got energy. Well, we know the energy in the charged capacitor, and we know the energy in the fully flowing current through the inductor. So probably that's just going to go backwards and forwards. Let's just see where we go. So our total energy equals the energy in the inductor plus the energy in the capacitor, and the energy in the inductor is given by that, and is given by that, and the energy in the capacitor is given by that. So let's have a look at what we're doing now. We're just basically saying the same thing again. So that's interesting. Okay. This theoretical circuit has no resistance, so no energy is lost to heat. So total energy is constant. So the rate of change of energy, not the total energy, but the rate of change of energy is zero. It's staying at whatever value it's at. So du by dt equals d by dt of what we just wrote down. And take out your constants. So you have L over 2 d by dt of I squared plus 1 over 2c d by dt of q squared. And we're going to represent I squared as I times I and q squared as q times q, because we want to play some game, I guess. And this equals L over 2, that's from there. And then, di times di by dt. And then over here, we're going to have plus di by dt times I. Okay? Oh, yeah, that's a bit of calculus coming in there, yep. Is that not an identity that you learn in calculus? Remember that? Okay, good. And then we have 1 over 2c, and then we're going to do the same thing over here. D by dt of that is q, dq by dt plus dq by dt of q. So then we simplify and rearrange, so the 2 comes out to there, and we have I di by dt and 2 dq by dt, and they're going to cancel, and that's going to cancel. And we get the Li di by dt plus q over c dq by dt. Okay, and then remembering that du by dt equals 0 because there's no change, and that I is equal to dq by dt, and di by dt equals d2q by dt squared. We set ourselves up with a differential equation, and we can we can divide by I and then rearrange, so we get this guy. d2q by dt squared is equal to minus q over LC, which equals minus 1 over LC times q. Okay. Now, I don't care about any of that really, apart from the final form. Look at that final form and think back about previously in our lives, and we did that. d2x, the acceleration, was equal to minus omega squared x. Do you remember that? We did that with the with the circular motion. Remember that? We had that guy and it was going round, and we'd say we want the x component of its position gives us displacement, and the x component of its tangential velocity gives us velocity, and the x component of its centripetal acceleration gives us our acceleration. Remember that? And we said, oh yeah, we can figure out that the acceleration equals minus omega squared x. Well, what they then say is, oh look, that is like that, and that is like that, so that is like that. And so we end up with omega is equal to square root of 1 over LC. So the angular frequency, the rate of oscillation of this electrical circuit, its frequency is equal to square root of 1 over LC. And if you want to plot it out, you know, you can say the current is going to equal minus omega q sine, like we did. So we take in all that oscillation stuff, and with a little bit of finagling, we're applying it to this. Okay. And I know this exists, but, you know, I'm not so worried about it. I just want you to know, yes, you can work out the frequency of the oscillator. You know, you can, if you know the inductance and you know the capacitance, you can figure out what the angular frequency is, what the radians per second is, and from that you could find the hertz of this system. Okay. And so this is, so then, all right, what happens if you're not starting off nicely? You don't start off just right? Well, we can mess about with that as a phase angle. To determine the phase angle, consider the solution of that, and we find a phase angle. I don't care about that. So on this, know that this exists. At the moment on this chapter, I'm not particularly interested in it. I might come back to it. Know we can do this page of math, but you don't have to be able to repeat it. Know this analogy. Know the analogy. Explain that to me in words. I'd really like that. If you can go through the logic of it, I'd really like that. Don't worry, just know that there is mutual inductance. Know there is an equation for mutual inductance. No, there isn't an equation for the energy. I might come back to this one. Know how to do this. And that. And boom, 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 boom. And know these earlier equations. These earlier equations matter. Okay? Cool. Let's stop there.